So I'm going to tell you about some work done in collaboration with Aldo Batista, who is a PhD student in the lab. And the work is available on arXiv under this number if you're interested in that. Okay, so what I'd like to talk about is actually some application of statistical physics to understand how multiple low-dimensional manifolds can be embedded into a simple recurrent neural network. And a lot of the motivation to do that actually, a lot of the motivations are coming from neuroscience, computational neuroscience. I will show a little bit of this motivation and maybe a couple of experiments to justify what I'm trying to do here. But in fact, even if we don't care about neuroscience, I think there is a very well-known hypothesis in machine learning, which is called the manifold hypothesis, or maybe I should call that the low-dimensional manifold hypothesis, that many high-dimensional data are actually intrinsically low-dimensional, and there are many good reasons to explain that. First, that could actually result from physical laws. If you take an object and make a 2D, make a photo from this object, then if you rotate the object, change the scale, make it further away or closer, and you can actually translate it and so on, then you'll get different pictures, but of course they are all related to each other through a few parameters. So that's why actually there is a low-dimensional manifold on which all these pictures are actually lying. This actually may be not exactly true, but it can be also only an approximation. And here are some examples from MNIST of the digit number 2. And there were some estimates in the literature of what could be the dimension of a manifold which is spanned by these digits. So whether we believe exactly in these dimensions is about between 10 and 14 or not, the idea is that you can have also some kind of local transformation, stretching, and so on, which would explain that actually there is only a few things you can do with the 2. So again, we get, even if the data are here very high dimensional, about 800 dimensions, then there might be only a few dimensions which are really relevant. And in fact, this hypothesis is the basis for many manifold learning techniques, and for understanding how you can actually also classify high-dimensional data with simple neural networks. And there will be a talk by Chaim Sopolinsky tomorrow, because if the high-dimensional data lie onto the manifold, what you have to do is to classify the manifolds. And we will probably talk about that tomorrow. What is important is that this hypothesis is not found only in machine learning, but you find exactly the same one in computational neuroscience, where if you, typically what you have to do in neuroscience when you do an experiment, you have a real neural network and you plunge some electrodes, here you see 3 of them, and measure the activity of the neurons. And what you see is that you may have different kind of activities in the population here, and you may actually find some modes, what people call neural modes or cell assemblies. And the whole activity of these very big neural networks with hundreds of thousands or tens of thousands of cells can be explained by the relative activation at different degrees of these cell assemblies. So here's an example with 2 cell assemblies, the green and the blue ones. And if you look at the spikes, which are emitted as a function of time of the different neurons which are measured, you could decompose these spikes here into some modes with some degrees of activation which vary over time. And that means that the activity, though being actually of high dimension in principle, lie onto a manifold here. So you can have a linear manifold, maybe more complicated model with non-linear manifold and so on. But we find again the same idea. So in that case, you could ask what are the dimensions along the manifold, and one of the hypotheses is that the coordinates along the d-dimensional manifold can have actually sensory correlates. I mean, they code for some external stimuli, and they can be used later on by motor cortex areas and so on to make some decisions and to produce some actions. So just to summarize this idea is that what we are interested in is that we have a recurrent neural network here, where the neurons may have some activities Ri. This is I is the index of the neurons. They are connected through some coupling Jij. And the n-dimensional activity point at any time in this very big space here, which is represented by the square here, is actually lying onto a smaller dimensional attractor, a d-dimensional attractor where d is much smaller than n. And by d-dimensional attractor, I mean that if I start from any configuration, it will relax after some time onto the attractor, and this is a fixed point, and I have a continuous set of fixed points along this attractor. And what matters here is what this coordinate along the attractor means. I can call it x, it's a vector in d dimension, and it could code for many things. So one possible application of this formalism comes actually from the representation of space in the brain, in particular in the hippocampus, which is a region, brain area, which is found in all mammals and essentially with some evolutionary variation in all vertebrates. And in particular in the region CA1 and CA3, people have found from the 70s the existence of what is called place cells, which are cells whose activity is actually related to the position of the animal in the environment. So if you have a rat moving in this square arena, for instance, then this particular cell in the hippocampus will fire when the rat is in this region here. It will be essentially silent outside of the region. This region is called the place field of this particular place cell. And another cell will fire somewhere else in the environment. Okay? So you would think that this cell actually essentially doing what I was showing here. I mean, they have an activity which depends on this coordinate here, which is the position of the animal. So in practice, how can we build a network, a recurrent network, which produces exactly this kind of behavior? So that's something which was proposed a long time ago, from the end of the 70s by Sunchi Amari, and there are more recent versions of that. And here I'm just copying some equations which I found in the paper by Sodit and Sejnowski. And what you need is, some kind of network. And this is very easy to write down. So here are the rate equation for the activity of neuron I. Ri would be its firing rate, so it's a positive number. And you get, if you forget about the G function here, you get a relaxation equation saying that at rest the activity would be 0 for each neuron. But then of course they are connected to each other through some couplings here, and through some nonlinear transformations. Think about some kind of rectified linear unit, for instance, rectified linear activation function. Then the activities of the other neuron J will be summed up, and then they will produce some inputs here onto Ri, and it will increase, Ri will increase its value over time. So the question, in order to understand the behavior of this network, is what are the values of the couplings? And essentially what you need to do is actually to have some mapping between the couplings between the neurons and the position in space they code for. So if neuron I is coding for some position xi in space, then you can build a network of Jij here, which is large and positive at short distances between I and J. So by distance between the neurons, I'm not talking about the distance in the physical space where the neurons are in the hippocampus, but I'm talking about the distance between the position they code for in the physical space. Okay? And then if it's negative at longer distances, you get excitation at short distances, inhibition at long ones. What you will create is a bump of activity that in the neurons which are active together are actually coding for positions which are close to each other in physical space.
Is there any biological justification for this form, and in terms of synaptic potentiation and so on?
You mean, do we have direct evidence from experiments that this is happening? Yes. No, there is no direct proof. Well, I mean, there is one direct proof in one particular case, not for the hippocampus, but for the elliptic body in the fly. There was a beautiful paper in Science 4 years ago by a group in Janelia where they could actually track. So so in that case for the fly, the collective coordinate, which is coded for, which is encoded in the network, is the head of the animal. Okay, so the animal is able to move its head with respect to some arbitrary direction in space. And what you can see is that there is a bunch. You can really see the ring attractor. And there are, I can show you some slides if you want about it. But in the hippocampus, this is just indirect evidence. So that means that if you get this bump of activity, suppose I arrange my neuron here if I have a 1D space, but of course you could generalize in 2D. This is very easy to do. So I arrange my neuron I's along a 1D line according to the position xi they code for here. So this is increasing order of xi's. So the neurons which are active at some time that are here, they code for similar position next to each other. And maybe at later time this bump has moved just by diffusion or maybe under some weak input, and then they code for another position here. So it's a way to move along the attractor here. Okay? So it's a neural representation of this mechanism. And now if I am one neuron, and if I look at the activity, then what will happen is that as the activity of the neuron as a function of this collective coordinate, which could be the position of the animal, will be almost equal to 0, except when x is close to xi, which is the center of the place field. And that corresponds really well to what is seen in experiments. Okay, so if we believe in this model, then we face immediately a problem, which is that we have a single hippocampus, at least in each hemisphere, but we have many, many environments we should code for. And so for instance, if you look at, if we, are in one environment, and actually the external situation, context is changing very fast. So here it's just a cartoon where you see, for instance, a predator coming in. Then, of course, the representation of the space should change very quickly. And this is known. Actually, there are beautiful experiments where you can see that even actually putting one object in one environment changes completely the representation that the animal can have about the environment. So that means we have a lot of representation for a lot of different contexts in a single environment, and we also have to code for many environments. So how can we embed many different d-dimensional attractors in a single recurrent neural network? So this is the motivation of the talk. So what is seen also in experiments is that actually when we change representation, we have a phenomenon which is called random remapping. That means that a given place cell will code for very different position in a different environment. So the same set of cells can be, by combinatorial rearrangement of a place field, code for many different maps, spatial maps. So the situation we are interested in is this one. We have a single neural network with some connections, and we have many, many d-dimensional manifolds here. And we would like to know how actually to embed all these d-dimensional manifolds in these neural networks. So our first solution to this problem was proposed by biologists, actually, by Sam Stanovich and Mac Norton in this paper in Journal of Neuroscience in '97. So it was a purely theoretical model. And what they did is that they essentially proposed an extension of a famous Hopfield model. So I guess you all know about the Hopfield model. So the Hopfield model is a model for memory of zero-dimensional attractors, fixed points of the dynamics. So you can extend it to d-dimensional attractors. And the idea is this one. Take the model I just shown with the Sodic-Chetnowsky equations and just pile so many models, many models of this kind onto each other, as you would do in the Hopfield model. So that means that if you have n neurons and L manifolds, mu will be the index of a manifold, each one of dimension d. And if you imagine that each neuron I has a place field in the manifold mu centered in some position xi mu, then what you can do is actually sum all the matrices you would have in each manifold, the one in the Chetnowsky Sodix model, and you just sum all of them, as you would do in the Hopfield model, okay, with the Hebb rule. And what you do is that this function has to be positive at short distances and negative at larger ones. So the main theoretical result that we have on this model, which is a positive result, is that if you set d to some number which is finite, and you send the number of neurons to infinity and the number of manifolds to infinity at a fixed ratio alpha, then there is a critical value of this ratio, which depends on d, such that if the number of manifolds is smaller than alpha c of d times n, then you are able to store the manifold. What that means is that in each manifold, or in most of the manifolds, you will be able to have an activity which is a bump, which codes coherently for position in that manifold. And eventually, maybe the bump will move and it will jump to another manifold and so on. But there is a major problem with this current theory, which has been going on for 20 years, is that the attractors are not flat. So the Sodic-Chetnowsky model is perfect as long as you have a single attractor. Because you see, you have invariance under translation here. That means if I take two neurons which code for two positions, then the interaction depends only on the distance. So that by moving a bump here in this landscape, then it's totally flat, and there is no change in free energy of the bump. Okay? But as soon as I have different manifolds, if I have a bump in the mu equal 1 manifold, then the other interaction here will create some interference, and the landscape my bump will see in the mu equal 1 manifold will not be flat. It will be rough, which means that if you are at, let's say, low neural noise, the bump will actually be pinned in the local minimum of this potential. So the attractor is not continuous anymore. It's a discrete attractor, which is actually rough due to the interference from the other maps. So this means that you have a very serious problem in terms of spatial resolution. We don't have a continuous attractor, we have just a few discrete points. Okay. So this is the major criticisms against this continuous attractor neural network theory. So what I would like to do in this talk is actually see how we can actually bypass this problem. Yes?
Is it clear that it's wrong?
Sorry?
Is it proven or clear that the landscape is wrong?
Well, we have some, in some specific models, we have studied the distribution of the barriers. Yeah, and it's really rough. And you can do simulation, you see that, yeah. Okay, so can we actually understand, by having this particular rule of interaction, of building interaction between the neurons, we are imposing, without actually controlling in any way, some kind of spatial resolution on the attractor. And we are computing for this particular spatial resolution, which is not really well understood here, the optimal capacity. But can we actually do better than that? Can we understand this trade-off between capacity and resolution? You could imagine that you could have a small number of manifolds which are encoded in the network with very high spatial resolution, so you have a perfect map. Or maybe you don't want that, you want many manifolds, but with lower spatial resolution. Okay, so the problem I'm looking at here is defined as follows, formally as follows. Again, I have n neurons, L manifolds of dimension d. I'm assuming that each neuron has a place field in manifold mu, centered in xi mu, and these are given. And now, instead of trying to learn the manifold with some a priori rule, which is not really good, I will try to learn some specific points along the manifold, which I call anchoring points. And I have p of them in each manifold. And so that means this is the manifold I like to learn, and I will just draw randomly some points, p of them here. And I will ask for the network to learn these points. I will be more precise in the next slide what I mean by learn. But if you do that, and if epsilon is the typical distance between two neighboring points, which is going to scale as 1 over p to the 1 over d, where d is the dimension of a manifold, then we will have some control about the accuracy of the coding. Because by increasing p, we will decrease epsilon, and we will control the spatial error we make in the coding. Okay, and then I generate data configuration in the n-dimensional space by using this thing here. So sigma I, which will be the activity value of neuron I in the muth manifold for the mth point, will be some function of a distance between the center of a place field here and the position of the point on the manifold. And this function phi is an indicator function. It's 1 if the distance is smaller than some cutoff, it's 0 outside. So here you have an example for, if I haven't made any mistake, n equal 5 neurons, L equal 2 environments, G equal 2 dimension, P equal to 3 points. So you see different colors. So each color corresponds to 1 over 5 neurons in the 2 environments. They have place fields here in the 2 environments, which are just random points. So each xi mu is the center of this disk here. Then I draw randomly 3 points, and I compute the activity vectors. Here you see the corresponding symbol of the points and the corresponding colors for environment 1 and environment 2. So you get this n-dimensional data point. And then now the learning problem is that one. I would like to impose that actually if I look at the dynamics of my recurrent neural net, just a simple dynamics where I have some weights here, and I have a function which is an activation function which is 0, 1. And then I would like that the data points I have created this way are just fixed points of the dynamics. So that means that if the neural network has this activity configuration, that should stay there. Okay. So, so there might be many solutions to this problem, because this problem, this learning problem, if you impose that, is a convex learning problem. So it's an easy thing you can do. And we will choose one particular solution, which is what we call optimal set of couplings, which maximizes this thing here. And this is very much related to support vector machines. So the idea is that if you look at the argument here of the minimum, you see that this is the argument of this function here times something which is 1 or minus 1, depending on whether sigma is you want to encode is 0, 1. So essentially what we have to do is we find in the n-dimensional space a hyperplane W so that all these neurons, the neurons with activity 1 in the pattern are on this side, the 0 on that side, and we want to maximize this hard margin here. So it's a standard SVM learning problem, except what is not really standard here is that we use it in a non-supervised learning context. Well, usually SVM, you map onto the label. Here we map onto the same activity pattern. So if you do that, let me show you some examples here. So here you have one environment with many points. I don't remember how many of them there are, maybe 200, something like that. And I will represent the active neurons, sigma equal 1 at any time, with a blue dot corresponding to the center of the place fields. And then what I do is that instead of having a 0 temperature dynamics, which is the true dynamics of the network, I put a little bit of temperature so that you see all the fixed points of the dynamics. You see how it wanders around. Okay. Okay, so you see, So this is a kinetic Ising model here. There is no equilibrium. The matrix you have learned is not symmetric, but you see this bump of activity is just moving. And at any time, most of the time, it can be pinned by all these red dots, but it's moving a lot, I mean, depending on the amount of noise you put here. So you see, essentially, it spans the whole manifold here, as you would expect. So now, more interesting, so what happens, you have periodic boundary conditions, so it goes through one side and comes back through the other one. So now, what happens if you do the same thing with two environments, or more environments? Okay. So you see, maybe it's not so clear, but you see sometimes the bump is here, and sometimes it jumps into that one, which means that when the bump is there, that means you have a cluster of points which code for similar position in environment one, and sometimes just through spontaneous changes, it goes into the other environment. That means that now the activity is coherent in the second environment, that the neurons which are active actually code for very similar position. And you can see the spontaneous jump from time to time. So you see this is in the second environment, no? Sometimes it's pretty bad because if it can be scattered on the four corners, but anyway. This is due to periodic boundary. And you see this forth and back process. Okay, so how is the resolution encoded by the number of, controlled by the number of points? So now if we want to understand that, we can do a numerical experiment where we set 0 temperature. We create a bump of activity in any position along the manifold, not necessarily one that was in the data set. And then we do 0 temperature dynamics, relaxation of a recurrent neural network. We see what is the set of active neurons, and now we decode the position by computing the center of mass of the centers of the place fields of these active neurons, right? And we compute the distance between the initial one and the final position of the bump. And if you do that, this is as a function of the environment for different number of points on the manifold. You see, essentially, it does not depend on the number of environments, but it decays with the number of points, as you would expect, and it decays according to the law we were expecting, right, as p to the minus 1 over d, which is what I showed in the previous slide. That means by putting more points, then you can control the accuracy of the coding. Of course, that has a cost, because if you put more points, this is more constrained to be encoded by the synaptic matrix, so at some point, it will limit the number of manifolds you are able to encode, right? And this is what we want to understand. So in order to understand that, we use Gardner's approach, in the first approach, but you will see it has its limitation, which is essentially an approach which was invented at the end of the 80s and which was mentioned by Lenka in her talk previously. If we look at the space of all possible couplings, the W matrix, then we have a feasible set of solution, feasible set here, which is all the set of solution W which actually have the data configuration as fixed points. And one of them here, in the center somewhere, has a maximal stability, which is the one we are interested in. So as we increase the ratio L over N, the logarithm of this volume is decreasing, and it shrinks to a single point. And that gives the critical capacity. And using well-known techniques from the 80s, we can compute that. At least you can write this as some kind of equation. And this is not a simple thing, actually. We have to compute the average value of some function over a set of p random points in the manifold. And to each point is attached a Gaussian variable. And all these p Gaussian variables are actually correlated to each other through this matrix here, which is the mu nu element of this p by p matrix is actually the function of the distance between the p points. And this function is essentially the joint area which is covered by the two place fields. So why do we have that? Because essentially, when we do the Gardner calculation, it's a mean field approximation which becomes exact in the large N limit. And we essentially have, suppose you have already stored L manifolds and you want to store a new one. Can you change a little bit the W's in order to accommodate for the new data points, the P data points on this new manifold? These are the P new data points. Well, you have some constraints due to the fact that you have already stored L manifolds, so that means you have, and these variables, Gaussian variables, are actually giving you some information about that, and you have to change a little bit your W's, and at some point it doesn't work anymore. So this F function, I don't write the expression, we have it explicitly, but this is obtained as a solution to a p-dimensional constraint quadratic optimization problem. So it's not so easy to do, but if p is not too large, then you can do that, and this is what you find. This is the optimal stability as a function of alpha for different p's. And of course, as you increase the number of points, then you have more constraints to satisfy, so the stability is decreasing. And in particular, the critical alpha, which is the maximal ratio of the number of manifolds per neuron, is actually going down. So the first line p equal 1 was computed 30 years ago, because in fact, if you have a manifold on a single point on the manifold, well, I mean, there is no correlation between the different points because you have only one. So that means this is exactly a set of random patterns that you have if all the manifolds are independent from each other, right? So this is that was computed by Gardner some years ago. But now what is interesting is that if you have 2 points, then they start to be correlated because they are generated from this low-dimensional process. Of course, if the place field occupies some area phi on this manifold, and if p is smaller than 1 over phi, typically, you don't see the correlation. So there is a crossover. P has to be larger than 1 over the area which is covered by the place field. So if P is large, then you will see very strong correlation here. And which means, in other way, that if I look at the critical capacity as a function of P, if P is not too small, not too large, sorry, I would expect that the patterns are essentially random. So the critical value of a number of manifolds over the number of neurons should be the value for 1 point divided by P. Because I add, with P patterns, I essentially have P independent constraints. So the number of manifolds should decay as 1 over P. But when P is large, I start seeing that all these patterns are correlated because they come from this low D space. So that means that when P is large, the patterns are more and more similar. So the capacity should decrease much more slowly. And what I am interested in is to compute this asymptotic scaling. The problem is that with the Gardner approach, we are not able to do it. So I'm not saying it's impossible, but I'm just saying we are not able to do it. Because this is actually a complicated expression. I was not able to extract the large P scaling of the capacity. So we turn to another way of computing, where essentially we average only over the anchoring points, these P points in each manifold, but we keep the input fields, the position of place field fixed. In that case, P is a parameter, so I don't want to get into the details. But essentially, we have to solve some equation here. And this equation has as an input here something which is interesting, which is a spectrum of a random matrix. And the spectrum of this random matrix is given here. So that means the following thing. You look at all the manifolds, so mu equal 1 from 2L. In each manifold, you have n points, which are the centers of the place field of these n neurons. And you have a matrix whose elements depend on the distance between points I and j. So when L is equal to 1, if you have a single space like that, a single manifold, this is the well-known random matrix, which is called Euclidean random matrix, which has been studied a lot in physics and math. But here we have so many spaces. We have L of them. The number of spaces is actually extensive in the number of points, which makes this ensemble rather interesting from a random matrix theory point of view. But still, using standard techniques for random matrix theory, from random matrix theory, we are able to compute this spectrum. And once we get this spectrum, then we can put it here and compute the capacity. And
but to compute this, I don't get it. You have no assumption at all on the manifold. The structure of the manifold we have a role on the spectrum of this thing, right?
Well, I'm assuming here. So I'm not sure what you mean by assumption. Yeah, so they are so for me they are just d-dimensional cubes.
Okay, then this is an assumption. Yeah.
Yes, of course, yeah. Okay, so so what do we get? We get, for instance, these predictions, which are, for small p, we see, since our theory is actually making some Gaussian approximation, it's not exact for small p, it's not too bad, even for p equal 1. But as p is increasing, it becomes really good, and I think it becomes exact asymptotically for large p. And the main outcome of this work is the following. We find that the capacity scales as some constant, which depends on the dimension of the size of the place field, over log p to the d, where d is the dimension of the manifold and p is the number of points. And I would like to interpret that as a positive result, in the sense that since we know that the spatial resolution epsilon decays as p to the minus 1 over d, that means that actually you can increase a lot your spatial resolution, decrease a lot the spatial error, at a relatively small cost in terms of capacity. So for instance, if you have manifolds, suppose you have a manifold you are at critical capacity alpha c, and you have manifolds with spatial resolution epsilon. And you say, oh no, I don't want epsilon, I want much better than epsilon, I want to go to epsilon squared. Okay? Then that means that the number of manifolds you will have, the maximum number of manifolds you will be able to store per neuron is going to be decreased by 2 to the d only. Okay, so you see you have a quadratic increase in here in terms of accuracy, and here you just lose by a finite fraction in terms of the number of manifolds. Okay, so so there are many things which could be interesting to study. So okay, as a summary, what we did is that we did an analytical study of the capacity versus resolution trade-off for the embedding of many low-dimension manifolds in a recurrent neural network. The model we have can be actually criticized by, or could be, let's say, improved on many different aspects. So for instance, we have a homogeneous d-dimensional cube for manifolds, so you could think of, let's say, more complex geometries. You could think about some sparsity constraints on the W, some element-wise positive constraint in order to have biological, plausible synapses and so on. You can think also about non-homogeneous distribution of anchoring points. That's a very important point. It's very clear from experiments that an animal which is actually coding for an empty environment is actually having some kind of homogeneous density of place fields. When you put some spots of interest in the environment, you see a lot of place fields which are dense around the spots of interest. That means the distribution of place fields is not homogeneous in reality. In fact, you can do that very easily in simulations. So let me give you an example where we do that for one environment. And you have all the crosses here, which are the positions that we would like to memorize. But we put also on the diagonal a lot of data points also. Okay, so we said, okay, it's interesting to be on the diagonal. And when you do that, what will happen is that the bump will essentially move along the 1D space here, and sometimes it will go away, diffuse a little bit into the 2D space, and will be attracted again onto the 1D line. So it looks like, it makes sense from a biological point of view if you think about the experiments. Of course, it's just the outcome of a simple model here. So, two other things I would like to mention. In the second theory we have, which is not exact for finite p, but I think it's exact for infinite p, we actually do not average over the centers of the place fields, which I think is interesting. So we have a theory which is valid for a given set of place fields. That's interesting because in experiments people actually can measure that. And so maybe we could see there is some kind of optimization about the position of these place fields. So the current folklore in the field is that when you look at one manifold and another one, so one representation and another one in a different environments, the remapping is fully random. There is no correlation at all between the two representations. But it's not clear that this is completely true. So it would be interesting to actually test that. So we could see actually move a little bit the position of the principle. We could see whether we could increase the capacity by moving a little bit the position of a place field, for instance, in our multi-space Euclidean random matrix. The last thing I would like to mention is the dynamics of learning, which we have not studied here. But I think it's potentially a very interesting problem because there are a lot of connections with very recent experiments on newborn animals. And I would like to finish by simply mentioning these experiments, which is a beautiful experiment which was done by the group of Dragoy in Yale earlier this year. So what these people have done is that they looked at rats between day 13, 14, and day 24. And they can actually record the activity in the hippocampus during 10 days. And day 13, 14 is about the day where the animal opens its eyes for the first time. And as soon as that happens, you can see place cells. And how does that work? If you look at the animal running along the 1D track here, and if you record the activity of some cells, you see that you can, so there were 36 cells which were recorded by multi-electrodes. You can see that the activity of the cells are, each cell, for instance, that one, will be very active when the animal is somewhere, let's say at 1/3 of the corridor here. Otherwise, it's more or less silent. So you can order the cells according to the position of maximal activity, which was actually what I call the center of the place field earlier in the talk. And this is what you see when the animal is awake and running along the corridor. So now what you can do also is look at the animal when it's actually sleeping, here before and after the awake period of running. And you can look at the place cells, so the cells which were recorded to have an activity correlated to the position during the awake period, but you can record the activity during the sleep phase, right? So you see the sequence of activation of these place cells, and then since you know to which position each place cell is coding for, then you can actually decode a virtual trajectory during the sleep. And then you look at what is this virtual trajectory actually look like, what does it look like? And so you see this is for day 15, 16, and this is for day 23, 24. So let's look at the beginning here. So along the x-axis you see time, and along the y-axis you see the center of mass of the active cells, which is a way to decode the trajectory at this particular time. And for very young animals, you see essentially that as a function of time, you don't see a trajectory, you see a fixed point. And as the animal gets older, you see, you see boots of trajectories here. So that means I would like to interpret that as the fact that the attractor, which is maturating during development here, is essentially corresponding to a discrete attractor with a few fixed points, one fixed point, maybe 2 or 3 here and so on, until it's becoming more and more flat and correspond to some kind of continuous attractor, the kind of attractors I was discussing in the talk. I think there would be a lot of things to do in order to try to model that, which is potentially fascinating. Okay, so I think I will stop here.